Dear students, in the previous lecture, we had discussed the search quality measure for measurement of the performance of the web search engines. But there were some issues. For example, the formula for calculating the document importance weight is an empirical one, although it makes sense, but it remains to be established as a standard formula. It is an empirical formula. Also, the weights over there, you have to adjust those weights, which is again taxing on the user. So we are looking to improve the web search quality measure by having a fuzzy measure. So we will see how fuzzy measure improves the performance evaluation of web search engines. But before that, we'll have to have a brief overview of our web search engine, of the fuzzy theory itself. Okay. So very briefly, fuzzy logic, it was started with fuzzy sets by Professor Lotfi Zadeh in 1965. We all know that a crisp set theory goes like this. If A is a set containing elements A, B, C, D, E, then A belongs to A, but G does not belong to A. Very clearly, there is a demarcation in belonging and not belonging, crisp values, binary values. But if we take the real life scenario in which I ask you if Mr. X belong to the set of tall people, you cannot say yes in absolute way, nor you can say no in absolute way. So you will start believing that there is a degree of belongingness when it comes to real life situations. Likewise, notion of intelligence, the notion of height we have seen, the notion of intelligence, beauty, they're all matters of degrees. And those degrees are highly subjective and perceptive. It varies from person to person. So in order to model the real life situations, we have to depart from binary logic and move towards fuzzy logic. I'll give you more examples. If I ask you a question, is 5 equal to 5? You will say yes. So truth value of 5 equal to 5. Very good enough. If I ask you, is 4 equal to 5? You will say no. So truth value of 4 equal to 5 is 0. If I again ask you, is 3 equal to 5? You will say no, and truth value of 3 equal to 5 is also 0. So now the people of fuzzy logic, they argue like this. They say that shouldn't truth value of 4 equal to 5 be less false than truth value of 3 equal to 5? Now you have to think over it. Even if you say that if it is not equal to 5, it is not equal to 5, how does it matter if it is 4 or 3? Then let me ask you another question. Shouldn't truth value of 4 equal to 5 be different from, what about truth value of 4.9999 equal to 5 versus truth value of infinity or minus infinity equal to 5? Then you will start thinking that 4.9999 equal to 5, that may be given a truth value, if not 1, something very close to 1. So that is the concept of degree of belongingness. Let me give you another real life example. Suppose a teacher asked in a class to define cat. One student stood up and said CAT, cat. Very good. You get 5 out of 5. The other student, he said KAT, cat. You said no, wrong, 0 out of 5. But then the third student gave the spelling of cat as PQR. Now you will start thinking that maybe KAT, cat, was at least better as a spelling of cat than PQR. So KAT, cat may get some marks, may not necessarily be absolutely false. So these are the situations where fuzzy logic starts gaining importance. So degree of belongingness is the membership value in fuzzy logic. I can say that Mr. X belongs to the set of tall people to a degree 0.9, to a degree 0.7, to a degree 0.4, to a degree 0.33, to a degree 0.21986, and so on. So that is when it is not completely true or false. There are truth as a matter of degree. I've given you the example. So if I plot it, truth value of x equal to 5, increased membership will remain 0 all through. At 5 exactly it will go 1, and then again it will go 0. In fuzzy membership, ideally speaking, it should be an asymptotic function, which is 1 at 5, but it should go to 0 only at minus infinity or plus infinity. At other values, it should have certain finite value, which is less than 1, no doubt. But then fuzzy membership, if you model it using an asymptotic function, which is exponential, that takes a lot of time to compute. So as an approximation, we can have a triangular membership function, which is essentially the linear function. So which will be 1 at 5, like this. And then at values in the very close vicinity of 5 will be close to 1. And as it keeps going away from 5, it keeps getting, it keeps moving towards 0. At something which is very far away from 5, it will also go to 0 if I'm taking an approximation. Right? In the exact scenario, it will be 0 only at minus infinity or plus infinity. So I'm just hurriedly taking you through the fuzzy membership concept. Now this example I gave you probably on the previous turn. What is the difference between fuzzy logic and probability? So if I give you 2 glasses of water, two glasses in which I say that membership value of water is 0.7, and there is another glass in which the probability of water is 0.7. What is the difference between these two scenarios? When I say probability of water is 0.7 means if you give me infinite such glasses, then 70% of them will have completely water and 30% of them will have completely something else. So 30% of those glasses will have completely something else. Whereas in the case of fuzzy membership, all the glasses, whether 1 or 2 or 10 or 100 or infinite, all of them will have 70% water and 30% something else. So there is a big difference between probability and fuzzy logic. Again, a realistic example, suppose I have to move from point A to B, say somewhere in Delhi. So there are 2 ways to it. One is a shorter way, but it involves a lot of traffic lights. The other one is the ring road. Now this ring road is a probabilistic path. If there is no traffic, you might reach in 15 minutes flat. If there is traffic, it may take 1 hour, it may take 1.5 hours, it may take 2 hours even. Whereas this path, you know that with the traffic lights, you can reach in say a half an hour. Right? So this is the probabilistic path and this is the fuzzy path. Also, a difference between fuzzy logic and probability, that for probability, the summation should definitely be 1, should exactly be 1. But that is not the case with fuzzy membership. The summation may not necessarily be 1. As you can see from this case, if you take the area under the curve, it will not be 1. It will be more than 1 area under the curve because it is 1 here anyway. It is already 1 here. So it may qualify to be a fuzzy membership function, but it doesn't qualify to be a probability distribution, right? Also in this case, if you want to keep the area in this as 1, under this curve as 1, then you cannot have the amplitude as 1. It should be infinite amplitude. Only then it will be an impulse function whose width is 0, amplitude is infinite. Then only the area under the curve would be 1, can be 1. So the summation of fuzzy membership values may not necessarily be 1 for membership values. I'm saying this because I'm going to use all this in the fuzzy search quality measure, right? So there are two words, graduation and granulation. Graduation and granulation. So fuzzy logic is all about that. You graduate. It is not a step from 0 to 1. It is either 0 or either true or there are intermediate values possible also. So that is called graduation. You have graduating values, gradual values. And granulation means you are forming clumps. For example, I can say that today is a warm day. Today is a warm day. So what I'm doing, I'm granulizing the temperature between something like 20 to 30 degrees, right? And if I say today is a hot day, that means I'm granulizing temperatures of 30 degrees Celsius and above. Okay. So fuzzy membership value, anything which is from minus infinity to 10 degrees, I can say that low temperature. 10 degrees to 30 degrees, I'll say medium temperature. 30 degrees Celsius upwards, I can call it as high temperature. So you try to form clumps or granules, okay, like this. So you have graduation and granule. Now, how are fuzzy logic and binary logic related? Binary logic operates in just 0 and 1. An interesting thing that I may have done when you were doing the logic theory course with me, if I asked you to read this, some of you might read there are 10 kinds of people. One who know binary and the other who do not. Then you realize, no, it is not 10, it is 2. This is 2 in binary. Okay. So that was just a light thing. Now there is so much success of binary logic by the use of digital computers. But let me tell you that binary logic is a very, very special case of fuzzy logic. Binary logic is, or let me say binary logic is just the boundary case of fuzzy logic. Fuzzy logic allows any real value between 0 and 1. Whereas binary logic works only on 0 and 1. So fuzzy logic is a very, very generic case of binary logic, or binary logic is a very, very limiting case for fuzzy logic. So now when I say that fuzzy logic is a generic case of binary logic, so fuzzy logic should be able to do all what binary logic does. For example, you do AND or and not operations in binary. So correspondingly, if you want to do fuzzy AND, so fuzzy AND will be min. Right? What happens? AND of 0, 1 is 0. So which is nothing but finding out min. OR is nothing but max. 1 and 0. 1 or 0 will be 1. The maximum not is 1. When I say that this is true, then the other condition would be 1 minus 1, which is 0. So likewise, if there is something which is true to a certain degree, say true to a degree 0.3, then it will be false to a degree 0.7. Okay. So all what we do in binary logic, we should be able to do it in fuzzy logic if fuzzy logic is a generic case of binary logic, right? So min, max, and 1 minus x may be a good starting point for and, or, and not. But then there are so many issues with them. For example, if I ask you to find out the min of 0.1, 0.9, 0.99, 0.999, min of this. So min of this will be 0.9, 0.1 only. But if I ask you to find out again the min of 0.1, 0.11, 0.111 and so on. It is again 0.1. So what is happening? Min function is essentially discarding the distribution of the remaining values. It is just picking out the min and it is discarding the remaining value. So likewise, max just picks up the max value, discards the remaining value. There should be a difference between these two data distributions, this one and this one, right? So for that, we need to have some advanced cases of operations, logic operations in fuzzy logic. Doesn't hold in binary logic because there is only 1 or 0. So we cannot have any other cases. But for fuzzy logic, we can have more cases for finding out and or and not. So for that, we have ordered weighted averaging operators. In fact, my 0th lecture, which I have given in the very beginning of this course, you should have gone through it by now. I had explained all of it there, but since I require it, that's why I'm repeating it. Otherwise, go through that lecture also. That includes so many more important things. So the ordered weighting averaging operators were originally introduced by Ronald Jaeger in 1988 to provide a means of aggregation. It unifies in one operator the conjunctive and disjunctive behavior. So this operator itself carries out and or operations. The OWA, in short, ordered weighted averaging, OWA operators provide a parameterized family of aggregation operators such as maximum, minimum, k-order statistics, median, and arithmetic mean, everything the same operator does. We will see how. For some n different scores, x1, x2, xn, the aggregation of these scores may be done using the OWA operator as follows. OWA of x1, x2, so on up till xn, these values may be given as summation I is equal to 1 to n wi yi. It is I is equal to 1 to n, like this. I is equal to 1 to n wi yi, where yi is the ith largest score from amongst x1, xn. Over here, the weights, wi's, they're all non-negative and their sum equals 1. Summation I is equal to 1. I will name. So what it mean? Let us take some special cases. Suppose I choose all wi's to be 1 by n. Then this very OWA operator, if I choose all these as 1 by n, it becomes arithmetic mean because it will be n largest, second largest, plus third largest, and so on. So it will effectively be x1 plus x2 plus xn, divided by n, which is the arithmetic mean. So the same OWA operator, by having different value of weight, I can get arithmetic mean. Certain value of weight, I can get arithmetic mean. Let me take a different value of weight like this. When W1 is equal to 1 and Wi is equal to 0 for all I not equal to 1. In that case, what will happen? I'll simply get W1 Y1 and W1 is 1, so Y1 only. All the remaining will be zeros because they're all zeros. All the remaining wi's are zeros. So it will become y1 and y1 is the largest. See, yi is the ith largest, so y1 is the first largest score. So I'll get max. Likewise, if I take wn is equal to 1 and wi is equal to 0 for all I not equal to 1, then in that case I'll get I'll get yn and yn is the nth largest of n values, so which means the smallest value, so that becomes min. So using the same operation but varying weights, I am getting different operations. So that is why I said it is a parameterized family of operators. Got it? Let me repeat. Using the same operator OWA but with varying values of weights, I am getting different operations. That is why it is called parameterized family of operators. The same operator with certain weights will give arithmetic mean. Same operator with different values of W will give me max, will give me win, will give me so many other values, which we will see also shortly. Aggregation by OW is always between the maximum and the minimum. That is the point that we must remember. The maximum value that it can give you and the minimum value. So all the OW operation will keep you between these two values only. Now, how to find the values of the weights Wi itself in situations where I don't necessarily have to get just max, min, and so on. For that, I'm going to make use of linguistic quantifiers. Try to see this. Relative linguistic fuzzy quantifier. The membership function of a relative quantifier can be represented as 0 if less than a, and it is a straight line r minus a, b minus b if it is between a and b. Sorry, this should be a and this should be b. In between a and b, if it is greater than a but less than b, it will be a straight line, and 1 if r is greater than b, where a, b and r, they're all between. So I can have several linguistic fuzzy quantifiers. For example, most. Over here, I am choosing a to be 0.3 and b to be 0.8. So whatever is before a is 0, between a and b, that is 0.3 and 0.8, is a straight line, and after b it is 0.8. At least half I'm representing by varying the values of a and b. A is now 0 and b is 0.5. As many as possible. A is 0.5 and b is 1. So slowly you can see that we are moving towards computing with words. Till now what we know is computing with numbers. 3 plus 4, I can say 7. 9 plus 6, I can say 15. But what if I tell you to find out most plus many? You will fail. You will say, what do you mean by most plus many? Right. So we are moving towards computing with words. I'll elaborate more on it as we proceed. As of now, try to understand what is relative linguistic fuzzy quantifier. I'm defining a quantifier as most, as at least half, as many as possible. Now, if I do it, I can find out their weights. Yaga computes the weights Wi of OWA from the function Q, this function QR, right? Describing the quantifier. In the case of a relative quantifier with M criteria, Wi will be Qi by M minus Qi minus 1 by M, where I is equal to 1 to M, with Q0 assumed to be 0. Let us take an example. It will be more clear then. The number of tracks is 7. What does that mean? I am dealing with two, ये वाला, ये हमारे पास 7 वैल्यूज हैं जिनको हमें OW ऑपरेटर लगाना है. I have to apply OW operator on these 7 values. So that is why I'm using the criteria M is equal to 7. And suppose I'm using the relative linguistic fuzzy quantifier most. I'm using this one, most. Okay. With the pair A is equal to 0.3 and B is equal to 0.8. The corresponding linguistic OW operator would have the weighting vector as follows. This table will tell you how to find out the weighting values. For M is equal to 7, the fuzzy quantifier most with the pair A is equal to 0.3 and B is equal to 0.8. So I will vary up till 7 because we want to have 7 weights. M is equal to 7, so we want to have 7 weights. I am keeping 0 because Q0 is assumed to be 0 and I'll need it in order to find out 1 minus Q0. In order to find out W1, I'll have to find out Q 1 by 7 minus Q0 by 7, right? So that is why I'm starting with 0. So I just numbered them and then I wrote I by M, which means 0 by 7, 1 by 7, 2 by 7, 3 by 7. M is a constant for our problem. 4 by 7, 5 by 7, 6 by 7, 7 by 7, right? Now, Qi by M is equal to QR. We all know. I just copied it. So let me correct it also. This is A and this is B, right? Now, Q0 is equal to 0. How about Q1? Q1 will also be 0 because I am at 0.143, which is less than 0.3. So less than 0.3, it will be 0. Again, Qi by m, where I by m is 0.286, will again be 0 because it is still less than 3. It is only when it becomes 3 that I by m becomes 0.429. Now I am in the linear range. I am in between 0.3 and 0.8. So I'll apply the linear formula now, which says r minus a. So 0.429 minus 0.3 divided by 0.8 minus 0.3. Again, we are in the linear range. So 0.571 minus 0.3 divided by 0.8 minus 0.3. 0.714 is still in the linear range. So 0.714 minus 0.3 divided by 0.8 minus 0.3. Now 0.857, as soon as I by m becomes 0.857, I have again exceeded 0.8. So I'm in this range. So it will become 1. And it will remain 1 when I by m is 1. Because this is again great point. So I have again listed these values. This is 0 by assumption. This is 0 because we are less than 0.0 because we're point is in the linear range. So just the calculation of this, just the calculation of this, and just the calculation of this linear value, right? And again, this is 1 because we are more than 0.8, and this is 1 because we are more than 0.1. So these QIs are formed. Now WI is so easy. W1 is Q I by m minus Qi minus 1 by m. So this minus this will be W1. That is why I require Q0. I don't require W0. It is not required, right? So I don't require it, but I do require W1. So W1 will be Qi by m minus Qi minus 1 by m. This minus this will be W0. This minus this will be W3. This minus this will be W4. This minus this will be this. This minus this will be W6, and this minus this will be W7. So I found out all the weights for the fuzzy quantifier most with m is equal to 7, right? Now suppose I'm given with values and I want to find out most of A1, A2, A3, A4, A5, A6, A7. So what I'll do, I'll multiply W1 with the maximum of A1, A2, or the largest value of A1, A2. So basically it is A1, A, W2, W3, W7 into descending sort of A1, A2, A3, A4 transpose. If I'm representing in the form of a matrix multiplication. This is a row matrix and this is a column matrix. So that is why this transpose. So what will happen? W0 into the largest. So W0 into the largest is 1, right? And then W1, so W0 into largest. Then W2 into second largest. So let me see what is second largest. Second largest is probably this one. Okay. So 0.00 into 0.637. W3 is 0.258. This is 0.258 into the third largest. So third largest is 0.523, right? And then W4 into fourth largest. And fourth largest in our case is, just hold on. Yeah. Okay. So this was the largest. This was the second largest. This is the third largest. This is the fourth largest, 0.342. 0.248 is fifth largest. Then 0.211 is sixth largest. And 0 is the smallest. So I just, what is this formula? This formula is nothing but the formula of OWA. Summation I is equal to 1 to n Wi yi. So W is from here. W is from here, and yi is the descending sort of the given values. So this is the ordered weighted averaging. So very surprisingly, I'm able to get most of this equal to 0.339. So now I'm taking into account the variation of all the values rather than just the min or the max. I'm taking the variation of all the values, right? So that is first thing. Second thing is that I'm moving towards computing with words. I'm able to find out the most of A1, A2, A3 and so on, right? Using ordered weighted averaging, right? So fuzzy logic in real life caters to uncertain, ambiguous situations, like the ambiguity in the case of our empirical formula. So it leads to artificial intelligence. What is artificial intelligence? Machine, we all know the very first definition, that which makes work easy. Then you have automation in the machine, repeatedly doing a job again and again and again without getting fatigued, without fail. Then programmability, you change a set of programs, the automated job changes. Then self-decision making capability. The machine must decide when to switch from one program to the other, or from one job to the other, one operation to the other. How can machine decide? So there we need the artificial intelligence. So computing with words, I'll give you the example of computing with words from the real life example of washing. What does fuzzy logic do in washing machines? A conventional washing machine, it is on the user to decide, to have a look at the clothes and decide what should be the wash cycle, what should be the wash timer, how much detergent to be added, what should be the temperature of water, how long you have to rinse it, and so on. But in a fuzzy logic enabled washing machine, you just have to give the inputs like this. My clothes my clothes are very dirty. So very dirty. Computing with words. I want them reasonably clean. So reasonably clean about the output. Linen is extremely soft. So extremely soft is the texture given to a machine, a washing machine in words. Now, based on fuzzy logic, the washing machine will decide for a very dirty cloth, for a reasonably clean output, for an extremely soft linen, what should I put as a timer, what detergent, what should be the temperature, what should be the wash cycle, and so on. Okay. So that is what computing with words is enabled using fuzzy logic. So now using this background of fuzzy search theory, we can have the application, the approach of fuzzy search quality measure. But I think I'll have to stop today for this lecture. We will take, with the background that I've given you today, we will take up the actual fuzzy search quality measure tomorrow in the next turn.